Environmental sustainability can both be achieved not just by institutions, but also by individuals. Today, we are already on our 5th session of our anniversary lecture series. To formally start our program, may we call on Dr. Sherdodinho Oy, Laboratory Head of the Data and Sensor Development Lab, to give his opening remarks and introduce our speaker for today's AMBAG session.
Good afternoon, everyone, and thank you for attending this 5th iteration of our AMBAG lecture series. So, I just wish to welcome all of you to this lecture where we are to gain a different perspective on disasters and hazards that are being influenced by our changing climate. So, I have been provided actually with the slides in advance, so I don't want to give away too much before Doc Greg delivers his lecture. But just to shortly say what it's all about, I just wish to convey that there's a really complex system on disasters, and the changing climate demands us to seek solutions quickly, rapidly, on how we should approach this problem. And more often, we need to think very much differently than we are used to in order to seek the solutions for this problem. Before I introduce our speaker, I would like to share with you a few things that I learned from the man who was and still is my mentor to this day. So, to help me demonstrate this, I brought 2 devices with me from 2 very iconic companies. So, do you guys remember this device? Would anyone remember this? iPod Touch, yes, that's correct. And the other one is, I don't know if anyone would know this, but I'm sure the brand name behind it is, it's Nokia. It's a Nokia Android phone. So why did I bring this with me? This is a really ancient one by today's standards. This came out about 15 years ago, but this only came out maybe 6 years ago, if I remember right. So why am I showing these 2 devices to you? Well, it got me thinking when I was just going through some of my old things at the house, and I saw this device and I realized that it's the iPod Touch was the first product that Apple launched that turned the company around. It's actually the iPod series. So before that, everybody was, I don't know, have their Walkmans and Discmans around just listening to music. And then Apple came in, talked to all these guys, tried to get a better understanding of how things work, both to the consumers, the record companies, and how do they deliver it. So what they did is they challenged the format, they challenged the industry. So they said, okay, we just need a really good format that everybody can use. We build a device that's really portable, and nobody has to bother with all these magnetic tapes and all this optical media that they have to bring along. So back then, you have to lug so many bags with you if you want to listen to a lot of music. So that changed everything. And they approached the music industry, okay, you price each song $1 and we'll put it up in a store. And it worked perfectly, and everybody adopted it, and as you know, all these media are gone, and all these other companies who produces music players, they all gave up. Well, except I think for Sony, they have a premium device, but it's essentially an iPod with a very good acoustic and sound card inside it. So that's Apple. So it was at a time that people were saying that Apple should just close down. And I think even Michael Dell said the best thing that Apple could do is give everything back to the shareholders and just shut down. He was quoted to say that before. So now we have this other guy, Nokia. At that time, Nokia was at its prime. So the problem with Nokia was, so they had control of all the mobile phones. Everybody was using it, and BlackBerry had some, of course, but dominantly it's Nokia who's dictating the game on mobiles. So what they did was, they just keep iterating this device. Okay, better keypad, a little bit of screen, a little bit of more memory, and that's it. And then when Apple came in and said, okay, we'll give you a device that is just touchscreen. You don't have to bother with all these buttons anymore. Problem with Nokia is they did the transition quickly when this technology came in. They were complacent, or maybe they were even afraid because they were used to doing something over and over again. They don't want to disturb the balance anymore. So here we are, 2025. The company who licensed Nokia name to build phones, they said that we won't manufacture this phone anymore. So no more Nokia branded phones will come out until, I don't know, if somebody is not nostalgic enough to build more phones that's named under the Nokia name. So what I'm trying to say with this is that it's quite the same with what we are facing with the climate emergency. We need to think differently. We shouldn't stay with what we're doing, to keep doing what we're doing. So the multiple disasters that we face require us to find solutions really fast with an approach that is unorthodox already. So these two that I showed you tell us two very different stories, and both have very different endings. So it's either we continue with what everyone is doing, or come up with something new. Maybe it's so new that people might say that's a crazy idea. I don't know what needs to be done. But what is really necessary is we need to keep Planet A running for the future, for other generations who will come to this life. So I got all of this thinking and ideas because of our speaker for today. It's because that's how much he taught me in the past. So I hope you also find these insights through his lecture for today. And his lecture for today will show you how to look at the problem in a wider view, and seek appropriate solutions for it. So now let me formally introduce our speaker. So Dr. Tangonan graduated with BS Physics from Ateneo de Manila University, and after which he returned to the US, got his master's and PhD in applied physics from California Institute of Technology, or Caltech. Then he received the Howard Hughes Doctoral Fellowship, and throughout his study, he became a member of the technical staff of the Hughes Research Lab, or HRL. Dr. Tangonan stayed at Hughes for 32 years and retired as Director of Research in charge of Communications Technologies. He holds 49 US patents and has published over 200 papers and presentations in a wide variety of fields. Then, after early retirement, so he decided that maybe he had enough of HRL, I don't know. So Dr. Tangonan was asked to join to be a faculty in the Ateneo. So here, he co-founded the Ateneo Innovation Center, where multidisciplinary projects in diverse fields have been conducted. Dr. Tangonan teaches the Innovation and Technology course, which he started with chemistry, applied physics, and material science students. So in recent years, the AIC has concentrated on disaster risk and resilience in the face of rising frequency and intensity of extreme events driven by climate change. The AIC research team on understanding risk of cascaded disasters has recent results that will be explained in this talk. So Dr. Tangonan and his wife Lori enjoy living in both the Philippines and California. And so, please, let us welcome our speaker for today, Dr. Gregory Tangonan.
All right. Thank you very much. I went to your heritage room, which is 101 to me, where I took a class from Father Miller, Father Badillo. Yeah. So I'm an old person. So I graduated, I'll admit to you, I graduated in 1969 in physics. I finished 2 years, my last 2 years here, but my first 2 years was in San Carlos. I learned so much optics in San Carlos under Father Ricard's, Father Bonengel, and yeah, in Cebu. And then I had the opportunity to come here. And yeah, it's nice to be back. So today I'm going to talk to you about, again, as Nino was saying, a very different perspective, okay? One of the lessons you can learn from Steve Jobs is don't work on what's obvious, work on what's the next wave. So let's talk about what might be in the next wave for all of us. And let's just treat this as a research. I'm really good at research meetings, so let's pretend we're all part of a small research group. There's nobody there on Facebook. We can just talk informally and everybody can relax, all right? We'll talk about the complexity of the kind of situation we're in where we have cascaded disasters. And we'll move on to a new kind of model that we have developed and we continue to develop together with my partner in this work, Dr. Lais Salvania. She's in the University of Connecticut now. She's a professor there. And we're working on this together. So we'll talk about this new model of self-organized criticality and how that differs from what we normally do. We normally do the Navier-Stokes and all that stuff. But that's not going to get us to those crazy events that we're seeing all the time. And then I'll reach out and try to say, you know, we work with the National Resilience Council and some of the people here, Joy is here. So how do we think or rethink a resilience in the context of these really nasty events? But also we realize it's not just the weather, it's our infrastructure. So we combine the two. Okay, so in a simple world, you'd get one disaster and then you'd have all kinds of time to recover. And every time it comes, you can recover. So you can develop a mentality that says, oh, we can build back better, okay? But if you have the other one below, where you get hit by an earthquake and all of a sudden you got these floods, and you guys have documented so many events like the bottom, then you don't have any time to recover. What you have to do is figure out, oh, I'm going to get cascaded disasters, and I may never recover. And I may not be able to guess what's going to happen next because these things are so weird, okay? So we need to understand that we don't have the luxury anymore of just dealing with one disaster at a time. The old statistics of 1 in 500 years, that's nonsense. When it's happening every other year, you've got massive disasters. So we're driven by two really tough problems. We don't understand where the energy is going in our environment. And the coupling is nonlinear. None of our models really works. And the disasters that we see, they get triggered, but then they almost have an existence of their own. Look at what happened. My sister lives in Maui. Okay, so it got triggered someplace, a spark from the power company, but nobody really minded what grasses there were in the area, and the winds were so darn strong, it moved so fast. In the case of the disaster, the fires in Southern California, very close to where I live, the embers were flying 100 meters ahead of the flames. So it is as if it created its own weather, but it was actually feeding on itself. It was a positive feedback, so strong that nobody could fly to dump the water. The firefighters just had to get out of the way, and they let it burn. So this is not your normal fire. This is something where it takes an existence on its own. It is its own dynamic. And you might say it self-organized itself into this nasty event that we call this storm. Oh, let me go, I can't go back. Okay, so you saw the thing on the right. So the infrastructure, we are critically dependent on the optimized infrastructure that we call supply chains. And one of the most amazing things that happened was the Ever Given ship. This is this is the biggest ship ever made, biggest container ship ever made to get through that channel. So when everything is working and everything's working just in time, it's these big guys who make an awful lot of money. But on one particular day, because the harbor pilot was inattentive, and maybe the pilot, the captain of the ship was inattentive, just a little bit of wind on this particular structure, before you know it, it was this, a very slight perturbation. If you want to call it the butterfly effect, that's fine. But that cost $40 billion, and they're still counting. So this is the kind of environment we're in. We don't really know what kind of events will happen, and we have a very fragile infrastructure. Normally we, in this place, think about the weather only, and we're already confused about that. But wouldn't it be nice if we had some way of also understanding how the environment collapses on it, kind of on its own? And we really have to do this, because if you look at our poor farmers, they're going through this kind of cycle back and forth. Excess heat, drought, flooding, bang. And then you ask the farmer, well, what's on his mind? He's got all these other things. But meanwhile, we're thinking about the weather. He's thinking about these things. Okay? So it's either we're going to grab the complexity of this thing, or we're just going to kind of ignore that this is what the real world looks like. And if you look at how well we're doing, this is an old chart from 2014, but I can't believe that we're doing better. We are failing these guys because we can't even tell them when the rain's going to come, when the heat's going to subside. So they're kind of on their own if it's a matter of forecasting. But maybe we should be actually forecasting fragility. Maybe we should be figuring out that this will come over and over again. It's not just a matter of winning one game, but it's actually participating in an infinite game. And actually, the end game is survival. So maybe we should think like that, because I'm certainly the farmers think like that too. So to kind of summarize this thing, you've got extreme weather, yes, but you've got a fragile infrastructure, and that you can explain what happened in Katrina. The levees were not really well cared for. The flooding was enough. It just popped. And then look at the numbers. Okay? So it's a slight perturbation, if you want to call it that, in the present. So it wasn't the super strong storm. So there's kind of a nonlinearity, okay? Even a glancing blow on some place that has a weak infrastructure can have a devastating effect. It doesn't have to be the weakest storm against the weakest part of the infrastructure. So we're left to ask ourselves, which side of this chart do you want to be? You want to stay on the attribution side, where you try to figure out how much of climate change contributed to what happened in Katrina or what happened in Tacloban or whatever, okay? And you use your old models. Or maybe you try to figure out can I actually figure out what might happen next? Most of us would like to be over there. By the way, most of the people in the public believe we're working on the right. And yet we're publishing stuff on the left. Okay? So that's the challenge for us, no? So maybe there's a hint of what's going on. And I'll show you this thing in a minute. But realize when a city is put together, and all the different pieces of the traffic, the power, all the communications, when a city is put together and it builds and builds, you build interdependency of all the subsystems. And so as a city grows, it gets more complex. You build a mall, people build. So you gradually build in complexity, and you keep optimizing so that you make enough money in the mall. People they buy a load every day, and even though it's not the fastest and the most efficient, but meanwhile the whole city grows and grows, but there are limits to the growth. By the way, I saw this number, 25 minutes to do 10 kilometers average. Somebody is publishing this, sitting in the Philippines. You know, the other day when we went to Ateneo, because my brother-in-law had a book launch, it took my wife half an hour to cross Katipunan to get into Ateneo. So we have crazy numbers. Nobody believes any numbers, no? Okay, so let's look at what happens on the right. So as the city builds, at the base, there's a certain kind of limits. At some point, you can keep adding grains of sand, and you get to the point where it's a perfect triangle or near perfect triangle. So if you start adding more, what do you see? You see avalanches. If you keep adding continuously, you see a bunch of avalanches, but they're not all the same. Sometimes they're small. Most of the times they're small. Sometimes they're medium, and sometimes, whoo, you can just see it running. So this is what we mean by self-organized criticality. At that point, it is quite unstable. It is metastable, if you want to call it. The slightest perturbation, and you see all kinds of crazy things happening. So you can see, oh, maybe I can use this for the storms, and maybe I can use that for the infrastructure. So let me just talk about the storms in a minute, but let me play a, want to time it, guys?
Imagine dropping sand grains one by one onto a table. At first, they pile up peacefully, building a small mountain of sand. But as the pile grows steeper and steeper, something magical happens. The sand reaches a critical slope where it becomes incredibly unstable. Now, adding just one more grain can trigger a massive avalanche. Small grains tumble down, knocking into others, creating a chain reaction that can cascade across the entire pile. This is self-organized criticality in action. The system naturally evolves to this precarious state where tiny changes can have enormous consequences. And amazingly, this same pattern appears everywhere, from forest fires to stock market crashes.
Wow, that's interesting animation. That's thank you to Dr. Salvania and the University of Connecticut. She shows this to a lot of people. And you can see that that is really interesting. Okay, but so let's take a little bit closer look. So we've had some of our interns in AIC just run a simple program. You can run a little Python program, just keep dropping sand, and the thing goes like this. And then all of a sudden you see these things, and you can measure the size of the avalanche. Really easy. And you get this crazy curve down here. You can see this power law dependence. Okay? This is log. All right? And the way you do that in the computer is to actually say, okay, each one of these cells can handle so many units. In the case of a city, it could be, I can handle 4 things going wrong, but I can't handle a 5th. Okay? And so here comes this grain of something that perturbs the system, and it perturbs 2. Now all these guys over there can only handle 4 max. So what happens then, boom, they all drop their load and they create an avalanche. Of course, in the early days, if there's just 111 down there below, you could drop 2 and then everything is okay. But you have a minor rearrangement. And those are the small earthquakes, the small avalanches on the side. And it's really important to have the small ones. Well, I'll show you that in energetics-wise. But the worrisome ones are the guys who are the big ones, who don't happen that often, depending on that slope. Okay, so you got this long tail, and there's the ones that were really worrisome. Those are the ones that are the killers. Okay, but you get the killers in the presence of all the other guys. Okay, so mathematically you get this power law, and it's part of complexity science. It has to do with this scale-free behavior of networks that are like small world, where they're really interdependent among one another, like we saw the malls and everything like that are all together. And some guys are more connected than others. So if you force a breakup, then you might break up into some pieces, but the guys who are really well connected may drag a whole bunch of other guys with them, and so you get these big earthquakes. And it turns out it's the power law. We'll talk a little bit more about it if you want. So you get this frequency of the avalanche, and you have this this power law. We'll talk a little bit more. So depending on the slope, if it's very fast going down, then in fact the chances of having a really nasty something happen, maybe like 1 in 10,000. But if the slope starts to lessen and the tail gets bigger, then in fact what was probably improbable before becomes inevitable. And we may be in that kind of inevitable state, both in the infrastructure and in the system. So we can do a simple model. Let's say I'm trying to figure out whether or not the National Resilience Council is trying to figure out, wow, this nice, well-groomed community, how do I characterize it? Well, you know, it's got a really nice slope because the power is under the ground and not too many people. And so maybe the alpha is something like this. So the chances of a big thing is really, really low, 1 in 10,000, because it's so pretty there, okay? But if you have another very informal community, it's a disorganized system, and in fact, there are very few common facilities that they have, then it would be very easy. The probability of having something nasty happen is much higher. So that's how these exponents kind of work. So let's go to and remind you, when that sand hits the pile, the reaction is instantaneous. And so we have to think about, well, so in other words, you have this metastable state, and I'm going to perturb it, and then it's going to what? Something will happen, no? So let's look at an example of superheated water.
Water heated in the microwave. Sometimes
heat it up. Okay.
Water heated in the microwave can sometimes explode. Because when water is heated in the microwave, it can superheat without appearing to boil. This means the water can become hotter than its boiling point without actually boiling. And when it is disturbed or a surface is introduced for bubbles to form, it can rapidly boil and release steam, causing an explosion. This can happen because microwave ovens heat water differently than traditional stovetop heating. In a microwave, the water molecules are excited by the electromagnetic waves that the microwave produces, causing the water to heat up. However, in some cases, the water can become overheated and superheated because it lacks the impurities and imperfections that would normally cause bubbles to form.
Okay. So normally we think of equilibrium, but this is a highly unstable, non-equilibrium situation. And what happens in that kind of situation when you've got this extra heat and all of a sudden it goes, you have an immediate avalanche. You have, nature tells you, we are going to dump that energy as fast as we can. There's no No, you can't wait. Let's let it diffuse. Excuse me. It's not going to happen there, no? And also, it's maximum entropy of production. So this is something we have to understand, and the model kind of gives us that. But let's remember that we have this metastable ocean. We really don't understand what's going on there, but there's all kinds of fluctuations there. And so one perturbation locally can drive the system into do crazy things. But it turns out that the eddies, one or two eddies coming together, is a perfect way of dumping energy. So the more eddies that you have, the faster I can dump it. Okay? The eddies form and they coalesce and they attract more warm water and then even moist air. And as they go there, the air evaporates and then they go up and then they condense and then they give off the latent heat, and then that actually increases the motion inward. So this thing is growing from the small scale all the way to the big scale using the same dynamic. Okay, it's the same self-organized criticality that's going on as you build from the early swirls that you see from the satellite all the way to the dominant. Sometimes it just starts, but it stops, and that's okay. Remember, the power law says a lot of these guys are the mini guys, but they are serving the purpose of dumping energy. But other guys find a right environment and they get bigger, and other guys really get big, and that depends on the whole area. So we shouldn't try to figure out how unstable this situation is, but you can see that this model begins to say, oh yeah, it's built in that the metastable physics, and it allows this growth in our understanding. So that's how it goes. It looks very much like the sand pile. And so you can see that it's growing through this, it's self-organizing, but it's the same dynamic no matter the scale. So that's what they mean by it's scale-free. There's no normal scale or no fixed scale. It just keeps on doing it's the same darn dynamic, whether or not it's 500 meters or down to the small mini cells that die. Okay. So I hope you get a sense that we could actually, if we looked at our data, we might be able to flesh out how frequently we saw these different storms and get that exponent. Nobody's going to do it for us other than ourselves. But to do what I would like to do, to create a damage, we're going to have to really understand what happens in the infrastructure. Okay? So let me tell you what we've been doing on the infrastructure. And I'm happy to show the picture of Lai and Harry and myself. We've been working on this a couple of years quietly. And we've got some papers. We studied air traffic and we studied power. Think about the infrastructure that we have. There are some hyper-connected places, critical pieces of the infrastructure, like airports, like power stations, that if they go out, they have a monster effect on a lot of people. So we started with, you look at the hub and spoke, oh my God, this is really, really wild. But you can think there are major cities, and then there's small airports that feed into the hubs. And there are also regional hubs. So it's pretty complex. And all kinds of things have gone wrong. I'm sure you all have stories, okay? I sat on the airport down in LAX coming over here, waiting for a couple of hours, and they told us they're changing the planes for some stupid reason, okay? But everybody is messed up. Or you go down to Jensen early in the morning, they have a big 747, and it's loading tuna. Not that many traffic guys going to Japan, but the tuna's going to Japan. okay? And it flies to Manila, and then it goes on to Haneda. And at so many points, this whole thing can collapse. So if there's delay in Manila, the quality of the tuna that we shipped goes down. Okay? So these things are all connected, and sometimes we don't talk about that connection, but it's the whole point of this is that they are connected. And if you look at some crazy things like CrowdStrike, who maintains the software for Windows machines, did an update, and then what happened? All kinds of airlines just shut down. In the Philippines, Cebu Pacific and AirAsia went down. Philippine Airlines that does Unix-based had no problem. I'll take on everybody else. It can happen anyway, no? And so, again, the system is so fragile that it can collapse. Sometimes it's weather. Many times it's weather. Okay? So how do we think our way through something like that? So I'm going to show you a result that we just got through publishing, which is done by Dr. Salvania. She took the data on the number of airports that were disrupted as a function of time, okay, and the frequency. Quite familiar, no? But nobody had ever plotted it kind of that way. So it shows you that we can understand these very complex phenomena using this kind of probability of, oops. So it gives you the probability of having these cancellations, but it doesn't tell us about the cancellation. In a deterministic way, you would want to, oh, this was what, because of this idiot did something like this. The deterministic world would say, explain it. This other world says, I'll just give you the probability, excuse me, I can't give you anything more. Because of the interconnectedness and because of the statistics of the way it's interconnected, the best you're going to get is a power law. Okay? And nature doesn't apologize, but this is interesting. So let me just show you.
We've seen how a single failure can ripple through the system. But what happens when we track every failure over time? Each time a disruption occurs, we count how many airports were affected. Some cascades are tiny.
Across the country. Now, we plot the size of each cascade against how often it happens. A pattern averages. A straight line on a log scale. That's a power. Power laws are the statistical fingerprint of self-organized criticality. Big failures still happen. They tell us that there's no typical failure size. Small disruptions are common, but massive cascades, while rare, are always possible. And when that rare cascade arrives, there's no stopping it. That's the danger and the lesson of criticality.
What's critical here is, let's say if you're running an airlines, there's so many things happening. How do I keep track of everything? How do I keep track when the Southwest went down, the software wasn't working? They couldn't figure out where the pilots were and whether or not those guys are ready to fly. Where are all the planes? So when something happens, there is a cascade of other things that happen as a result. So depending on that exponent, you get all kinds of crazy things, no? It's subcritical, it's not so bad, and depending on how it moves, you get different things. But realize in a power law arrangement, there's good situations like above 2.5 where you have a nice mean and you have a variance. But as you vary the slope, then the mean goes away and the variance goes away, and almost anything can happen. And that's what that thing is saying. But Lai was able to create her own sand pile for this, and she was able to tweak the fragility. We can now examine the, if you want to call it, the vulnerability matrix of this kind of hub and spoke. And you can vary it in different ways in the subcritical, and you can actually predict different kinds of behavior. You know, the original stuff we do, this was just data that we got for free, but now we're using our own model to ask very different questions. You know, which are the most vulnerable airports? Or if Atlanta goes down, what will happen? Who's the next one who will go down? Or if there's a storm, if we put in the seasonal value, and there's a storm in Colorado, how does it bring everything down? Who's interested in this? Obviously the guys who run the airlines, okay? Obviously the insurance companies who are getting money for business continuity. So if they can understand how much it costs every time it goes down, they can actually anticipate what might happen. If you ask yourself, it's kind of magic, no? But if you realize, this power law is kind of magic, but if you realize this is just one of what we call the maximum entropy distribution. If all you know is a mean, the only way you can plot the data is by an exponential. That's the best expression of what you don't know. Okay? If you have the mean and you have a variance, the only way you can express what you know is a Gaussian. Okay? But if you have this scale-free invariance thing, and what's constant is the log, you get the power law. It's just kind of interesting, but we never think about it when we know that we actually talk about it when we do statistical physics, because this is part of complexity and it's not part of statistical physics, I guess. Okay, so just a reminder of that. So we applied it to power, as I said. So this is data that we get on the power in the Texas grid. And you can notice that the exponent is, on average, is around less than 1.5. So the Texas power grid is not a very robust place and when it goes down, it goes down really bad. So this is the number of customers that are affected, and that's the critical exponent. You can see that it dips very badly, but you can also see there might be some early warning in this kind of ahead of the disaster, and here we are in looking at Florida, and you can see the incidence of the hurricane, and then they're down. But even before, you kind of know that these guys are in a very precarious situation. It's not this really robust exponent of 2.5 or 3, okay, which you might see in Europe or someplace like that. So I hope this helps you to see that we could probably do the left side. If our ambitions was to try to use AI to calculate not just the storm, but actual damage, we might be able to do both, okay? Both kinds of power, and then bring them together into a damage. And why would we want to do that? We need to take anticipatory action. If these things are happening and it's so crazy, and it might be an infinite game that we're in, the smartest thing for us to do is to anticipate the worst and try to figure out how do I harness the water, how do I do this? And that's where everybody is moving now, okay? But most certainly if we can predict the damage, there are a lot of people who are interested, especially the insurance company. So Dr. Salvania is at the University of Connecticut. Connecticut is the home of insurance. and so, okay, and so anticipatory action, and so another way of looking at it comes from the National Resilience Council, is that as opposed to just going into relief and others, we gotta figure out how bad it could be, and we have to get ahead of it. So maybe we can use those projections that we have and an AI system. But other people are taking anticipatory action. If you look at Hamburg, Los Angeles, north and south, in one of those atmospheric rivers, LA County got about a third of their water supply by harvesting all of that rain, which is amazing because they had a drought. So they've kind of changed the equation, no? China is doing that. Sponge cities that actually have porous kind of pavements and absorb it. Okay. Of course, we have the Global Fund for pushing renewables, and this is on Facebook Live, so I wonder what's going to happen in the U.S., but it's a different story. And then, yeah, well, right. I'm just going to, I'll look as American as I can. Okay. So, and then, of course, the resilience hubs, no? We're working on resilience hubs. But, you know, there's some intriguing projects that are going on. One project is, can I float solar panels on a lake? And the project we're looking at is Laguna Lake with a partner, SunAsia, and they want to put gigawatts on the lake. So this is a nice problem for us to look at. So we have kind of looked at it with the guys in AIC, Tess Perez, Leah Macaraig, Toby, all of us, because it's Laguna Lake. And so we came up with ideas that, you know, what they're afraid of is that when the winds get high, the waves get, the whole thing will break. And there are many cases of it, especially in Japan, at least 2. All right? So the proposal here from AIC is to put floating gardens around it, the sub-arrays, and the floating gardens like pontoons with dampeners, and we lash it to there. But the gardens actually clean the lake. This is not the cleanest lake in the world. And so we will have floating gardens in the normal times, but when we expect the winds, we will lash them and we'll hold them there, and we'll have the dampers. And then we'll take some of that energy and bubble, micro bubbles down there to rehabilitate the lake. It's just a small fraction, doesn't take that much. At the same time, we will have field servers that will measure DO as a function of depth, everything. So it's like a floating lab. Maybe we can build this together, okay? So that's one kind of project. The other project that we worked on is the resilience hubs, and thank you, Joy, who's here from the National Resilience Council. So we're trying to accommodate at least 100 families. So what is the next generation evacuation centers? I think there may come a time when we have a legislation that every major city has to have a really world-class evacuation center. So what are the components of this? We make sure that there's food, energy, and water, and we have connectivity. We put in Starlink. Starlink is baseline, and we can talk about the services. But we actually, with the Starlink inside, we can achieve a whole lot of services. We have our near cloud in there. You can do telemedicine from there, so people who are not so trained in emergency medicine can have the benefits of a doctor nearby, working them way through. We also have gardens. We have enhanced situational awareness because we can now unite families much faster than anybody before using facial recognition and others. So we're working on that. We're working on other services like Lockbox for families, where all your valuable data is stored, and you have your blockchain security. But the real problem has happened after a disaster. Many people have to re-identify themselves. In Tacloban, you had to prove that you didn't get money from somebody, some other agency, before, and you were not an interloper there, you had to prove who you were. Meanwhile, you just saved your life. The last thing on your mind was getting ID and all that stuff. So we're making a lockbox. And there are new vulnerabilities. If you think about what happens at the airport, Hong Kong, recently, heavy rain, it happens all the time. The runway disappears in heavy rain. And that's why Nino and Matt and I, we have visibility cameras. We're trying to understand how visibility diminishes in heavy rain, because there are crashes all over. And we developed a way of making it really easy using just smartphones. So these are the kinds of vulnerabilities that we have to anticipate, that we can probably work on it together. So I come to the end. I've kind of told you about this crazy model. I have told you that it actually helps us to understand, or reminds us about the nature of how these storms grow. And it also tells us that we can't neglect the fact that our infrastructure is fragile. And what we see every time there's a disaster is that we have a new fragility. I didn't know that the pumps weren't big enough, and that's why UST is always flooding. Somebody has under-engineered the pumps, okay? Or the pumps aren't there or something like that. But every time we see this vulnerability, and the smarter way is that let's try to figure out our vulnerability. And so we are working with people who are thinking about parametric insurance. So I pay you ahead of time to fix you up, but I'm not going to pay you when there's damage. So it's kind of an interesting thing. But one of the charts I showed you, that the government may have to be the insurer of last resort, but there is an interim place where we could actually design insurance so that insurance companies can stay in together. Come on. But that's not the last chart, because I know this is interactive. So if you didn't have any questions, you might want to pick one. It may be really good to ask the professionals here, why is it so hard using our present tools to predict these extreme events? And why do you have to use some crazy model like the sand pile model? Okay? Or you can do anything, what is anticipatory action, things like that. Again, thank you very much.
Thank you, Dr. Greg, for that very insightful presentation. I've learned a lot, and I think the audience also learned a lot as well. So now, we are opening the floor for questions. Viewers on the live stream may also ask questions by typing them in the comment section. Mike, can you please hide Mike?
I'll start it off so that sometimes it takes some criticality before.
Really? With Ateneo?
Actually, I can answer a bit the first question, because the answer to that question is related to my question. It's difficult to forecast weather, period. Lorenz, in the 60s, in MIT, he just took a break, right?
University of Santa Cruz.
Sorry, yeah. He just took a coffee break and came back and saw the results diverge. So that's how chaos was started, because of these non-linearities. So chaos. And you see these Lorentz, what do you call them? Those Lorentz. right? They oscillate. My question here is the sand thing is interesting, but you just have I guess a stimulus that's small. If we look at carbon dioxide in the last 800 million years, if you look at the paleoclimate, you see these oscillations of carbon dioxide. They usually track temperature. When it's warm, carbon is high, very stable. Then it plunges to another state, an ice age. It's very cold, carbon is low. The rates of change, the rate of change of CO2, okay, when CO2 rises during an interglacial period, it's not steep. It takes several thousand years. So the trigger is slow by glacial scales. What we've done in the last 200 years is we're now at 420 ppm. Pre-industrial, we were at 280. That's just 200 years. That's a spike, not a gentle slope. So it's not actually just a grain of sand. Do you see what it's what we're dropping is a stone. And so you wonder how stable the climate will be. Now, the one thing that we're afraid of is a low probability but high impact event, which is the collapse of the Atlantic meridional circulation. Have you heard of that? Because there's this current that brings heat, back in the Atlantic. If that collapses, of course we don't tell this to everyone. Facebook. God.
So now they know, Father.
I mean, we don't usually think about this, and I guess because it's frightening, but someone has to think about it. It's a low probability, but high impact event. It's not going to happen probably this century, but it can happen in the subsequent centuries. When that collapses, things will go haywire, actually. It's one example of a tipping point. And there are many climate tipping points, right? But this is important, what you just showed us, because you've shown us because of the transition. It's amazing because parang ano lang di ba? It's just a simple graph. Frequency tsaka number. Log, power. May physics ba yun? Entropy lang.
It is complexity. It is the small world network of interdependent pieces forming this network. And when that small network breaks, it breaks up into pieces. It's the same. So the power law comes directly out of the fact that that there's the same mechanism for it to break up is the same mechanism for the whole thing to break up. It's common, and there's no scale, fixed scale over which that works. It's the same dynamic from the eddies all the way to the low pressure that's formed, all the way out to the big superstorm. It's the same dynamic no matter what. It's 10 meters all the way up to 500 kilometers. It's the same coherent thing. So that's why it's a very good example of self-organized criticality. Okay? Yes. Yeah. And so it's like, surprise, surprise, you get that number, and that number is a probability of having that kind of event. So that's why I said, if we can get our data on some curve, we might figure out what our slope really is. Okay? And we can do this for the infrastructure. We can pick power, or we can pick I think we can get the data from the airports. We can get our own data, or we can start working as if we're an ASEAN institute doing extreme events, and we can go work together with the Indonesians, Malaysians, and try to figure out what's different in our environment that's not in Norway or something like that. Again, it's for us to decide. Okay, what do we do next? Yeah, but I was amazed, and actually when Lai showed her results to me and showed it to other people, we had all kinds of other people asking us all kinds of other kinds of questions, because this works very well in social systems. So we are studying trust systems, how trust systems actually can you build to a certain point, and it doesn't take much. Somebody gets it in their head that to defy the laws of economics, and then everything falls apart. So it applies in so many different ways, and yet because we understand our linear equations very well, and we're content to do ensembles, and we fudge with all the parameters, we don't necessarily take this radical approach. And it is radical in that sense, but the reception that we've gotten all over the US, even the power companies and insurance companies, that this is something they've been looking for, a probability of nasty events happening. And we could change it. We could say, what's the probability that an event will happen, but it'll cost you $2 billion? If we had that data through a partner, we could actually calculate things like that. So that's what's, you say, wow, I got this number. I don't know where I got it from, but people, it's good enough for a lot of people to decide whether or not should I be in that insurance business in this particular area, or companies like power companies have gone bankrupt because of the wildfires in California. So the business interest comes very quickly when you've got these kinds of models.
Thank you very much for your very interesting talk. I'd also like to follow up from what Father Jet also mentioned about global warming, because it's also a cascading event. And with the model that you're talking about, it might be also nice to include in those paleoclimate data. I come from the geology and earth science perspective. To increase those data points, we look into the sediment and rock record. For those, example, mid-Holocene, 5,000, 6,000 years ago, it was warmer than today, and that's what we're forecasting. Sea level was higher than today, and what were the storm sizes or frequencies, and we could probably see that from the sediment record. For one, I am a geochemist, so I do this paleoclimate analysis. And for example, for the Laguna Lake record is really, really nice because it's lake and the sediment accumulation is, it's high sedimentation rate. Sediment accumulation is really nice. So we could look back even beyond the Holocene in there. And we've seen those, the rise of the Anthropocene, for example. So it might be nice to merge with the paleoclimate data and the forecast and the current data that we have.
This is just kind of like a model that you guys can apply in so many different ways. We focus on quasi real-time things, for which insurance companies and other people are very interested in, and also our resilience partners on national resilience. We're trying to get communities to think about the disasters. So much of what we do is still one disaster at a time. And the logic that says we can build back better, I'm not sure. I'm not sure. Okay?
I agree, yeah.
And so it's either you're going to understand that it's not a one-off game, oh, we won this time, or you're actually part of an infinite game. Okay, and there it's not just winning; it's actually surviving. So it's kind of scary that we put it in those terms, but we have to. If you've got 20 typhoons hitting you every year, maybe that's the better mentality. I'm part of an infinite game, and let's figure out who's changing the rules, and let's make sure that we anticipate a new vulnerability. As I said before, every time with a disaster, we find hidden vulnerabilities, or we just pretend that the big earthquake's not going to happen. We behave as if the risks are zero. Good luck.
Thank you very much. I'm very interested that you have data back millennia years, and I'm thinking to the Anthropocene. I'm thinking about Laguna Lake being extracted with so much water, and I worry that like Mexico, they lost their lake. So I'm thinking, can you project it to the next 100 years? How much water we will have in Laguna Lake? Because, I mean, Mexico used to have a lake. But because of over-extraction and the drought, you don't have any more lake. So I'm afraid we might not have Laguna Lake in 2200 or 2100, I do not know. But I'm also thinking about so many users using the water. And the replenishment, I worry, the recharging is not enough.
You mean users and abusers?
Well, I'm trying to be diplomatic. So I'm thinking about...
It's okay, I'm leaving, so...
Yeah, we're in Facebook Live, and I've learned if you want to work with people, you don't say anything not so good about them. No, but really, it's a worry. I want to put a challenge to you.
Okay.
Do the modeling.
Yeah. Well, we've had a lot of this. This is a very interesting model. It has so many aspects, and I wish Lai was around because we have been fielding all kinds of questions from all kinds of people they say they have all the data in the world on water, and they're asking us, can we use this kind of historical data or real-time data to predict some different kinds of vulnerabilities. If you take the power data, for instance, you can look at the power data that we saw of this thing, and you can ask kind of a crazy question. You can say, I wonder if there was a hacker and they were playing around. When the lights go out, could they be testing some way of inhibiting our recovery during software or whatever? And can I see that in the change in the exponent? That's the kind of crazy question people ask when they see this kind of result. They don't just look at it, oh, that's interesting, but then other guys walk away and then they ask a different question. Can you see on a time scale of a few weeks that their recovery has been affected by something? Like the recovery of an airport is changed when it's a software glitch or the power went out and it just came back, or the radar came out. So what's the time scale of the recovery? So yes, it goes down, but how does it come back up? So you can get that, and we should be looking at that. Supply chains. We have so many supply chains, so many that go down. Who are the guys who really know? Procter & Gamble. They know how fast it went down and how quickly they were able to get back in business. And yet, that's not part of measuring the weather, but it's certainly part of our understanding of how these systems relate. And so, again, like what Nino was saying, we got to do different things, or maybe we have to ask different questions, and we've got enough brain power. We're just not asking the right question, maybe.
Yeah, well, this is a stupid question. Can you plot waste management versus floods?
Management.
waste management versus flooding, or infrastructure versus flooding.
Oh, yes, yes, yes.
And when you have a criticality.
Yes, so it's not uncommon worldwide that when there's flooding, that the sewers back up. And then you have leptospirosis and everything like that in it. You think that it only happens in Asia, and now it's happening in Florida and all these other places. And so the engineering of those pumps, the under-engineering of those pumps cause all kinds of grief on the backup. So I think everybody's looking at anticipatory action, and one of the things is to figure out the strategy, because I can engineer for a certain kind of rainfall, but if you've got this kind of guerrilla rainfall that we've got, where 50 millimeters per hour for several hours, nobody can handle that. And nobody's sewer system is actually can handle that. So we are entering into really nasty territory. Father will tell you, whatever we're seeing now is the result of what we put in the environment up to now, and we can't even figure that out. Imagine what happens if we keep on going. So that's why this anticipatory stance for us is really smart for us to think about that. What regime are we in? Maybe that's the other thing. That we have to look at our infrastructure, and we have to realize it is really quite fragile. We just keep optimizing it so it works, and we patch it up.
Can I follow up with Toby's question? The other day, Tipolo, Mandawi got all flooded. Cebu City, 3/4 flooded. And I asked the local, and he says because the riverway or the waterway was claimed many years ago. So how, I'm thinking, using your model, how to protect, the waste, the reclamation in the coast, the runoff from the mountains, the deforestation, this permutation of several factors that will lead to it. How would you, if you were to, because most cities now in the Philippines are really flooded world over because they developed the uplands and they did not do the engineering and infrastructure base accordingly to the expansion. So again, I challenge you, Greg, do the model.
It's not me, it's all of us here, no?
No, because they're having a water summit now, simply to respond to the flood. But they're only focused on garbage. I told them, as long as you continue put residential subdivisions up in these fields, and you continue deforesting, you'll never solve the flood. But they're focused on the garbage, and they're blaming the poor there for the garbage, when actually it comes from upstream, downstream. Systems thinking.
So think about it. I'm talking about, we're part of an infinite game.
Yes.
And we are consistent losers in every episode. And so I don't know how to get out of it, but I'm not the doomsday sayer or something like that. But
systems thinking should be taught in every.
well, yeah, this is our version of AIC's version of systems thinking, no?
I just came faculty day. We're all just interdisciplinary, when we should be inter and transdisciplinary, vertical and horizontal.
All the discussion is very exciting. Another interesting model, probably, since it's still being built, is the Bulacan International Airport. Since it factors in the flooding, the weather, and not just that, you've mentioned groundwater extraction, which will not only affect the areas beside it, but like a lot of the coastal areas are just delta plains that used to be built by mud, and with groundwater extraction, we cause subsidence. So I guess that's one, and yes, plus sea level rise with the modeling with the high tide and low tide. And recently, like last year, including the oil spill. So I guess that would be an interesting modeling.
So you
for-
notice what Dr. Silvania actually did. She built the model from scratch for the airlines, built the model from scratch for the power lines, and then you can put in the vulnerabilities. So we could do a model for Cebu of the water availability and the waste management and the fact that they've got desalination plant, but then half the people are working they're on wells of dubious quality, and so it is as complex as that. But we just have to write that into in some kind of model, and then we can do a what if. What if there was this perturbation? So it can be done, but it's an enterprise that we should do. Nobody's else going to do it for us.
Yes, yeah, I agree. Also, the Bulacan International Airport.
Yeah, that's a very complex situation. Okay.
Any more? Oh, Doc Celine.
Hello. Very interesting, Dr. Greg. How would you, when you say, first question, when you say there's no scale, you're talking about time scale, spatial scale, both?
It's spatial and temporal. If you think about what happens inside the early, as soon as the perturbation hits inside the ocean, okay, in that area, then small eddies form, okay, and then they start to coalesce. They get bigger and bigger, and then it continues. It's the same mechanism, same physical mechanism, same spatial temporal difference. It may be happening faster, or there may be many more of these guys dumping all the heat, trying to form larger eddies, but meanwhile, they're dumping all that energy, creating all that entropy. So that's why there's so many little guys. But then it will grow, but it'll grow slower, but for its size and its shape, it's actually consistent. There's no preferred size of an eddy. Okay. This thing is growing, but it's growing with the same mechanism. So we shouldn't be surprised that there is some structural, statistical insight that you can grab from that, and it turns out it's that darn power law. Okay? We can hand wave all we can show the math, but it's kind of like that. That's my hand wave.
The second question is, can the model resolve multiple cascading disasters? Multiple?
Well, each one of these avalanches can be thought of as a cascade. Yes. Okay? So what might be characterized as one big typhoon, but could be actually a typhoon followed by flooding, by this. And so the cascade, the avalanche actually can be multi-component. All right? So what happens is that you've got the buildup of this storm, and we can watch it, and with AI we can figure out what the heck happened. Okay? We can guess. Then when it hit a certain area, then we have to understand the vulnerability of that area. But let me stop for a second. We are looking for partners like a Google, other people who are doing AI, who see that this kind of model and their ability to gather all kinds of data, we might get very high resolution understanding in time and space of that exponent. All we did was we took available data. But if you had a partner, and we're looking for different partners, who wants to become an AI center, this is one of the things that they could easily do. Study extreme risk. Okay? So we are very interested in talking to partners in Asia, and maybe we could develop this kind of modeling. But we will have to take a heck of a lot more data, or review a lot of the data that we have and see even in a crude way we can do it. But if you want to do problems like Cebu, it's the guys who have the data. I'm standing in a place that's got all kinds of data.
Doc Ruby.
Thank you, Doc Greg, for the excellent talk. So I went to the bathroom and I was thinking about your talk, and then I came back. I have a question. Oh, this is in Facebook Live. Sorry. Okay. Anyway, so Doc Greg, this is it. So my understanding of the model and also the plot is that it's like a histogram. It is a histogram, but it's a log plot. Am I right? Yes. Okay. So the frequency on the y-axis and the event. Okay. Intensity or number?
The size of the avalanche.
Yes.
Or the
Okay.
damage
Or the
caused
disaster, or on the in the x-axis. Using your model, or did you ever look at the rate of formation of, because that's the next step that came to mind. How quickly the big event actually happened using a tiny stimulus.
Okay,
The rate, it's like position versus time, but now I'm asking about velocity.
Well, no, I get you. I think I understand, and that's why I showed that that example of the metastable overheating of the water.
Yes.
Because the dictates are that it's maximum energy dissipation and maximum entropy. There is nature doesn't allow the system to say, can we do this slowly? So it happens instantaneously.
Instantaneous, okay.
And we don't really, and you can't get that in the other models. The other models don't allow you that kind of opportunity.
Okay.
And so it's those opportunistic perturbations, like the swirls, that actually gather all of that energy faster than anything else. And that's why you see the swirls first, and then the plumes going up, and then you see the atmospheric river or something else, okay? So it's a good reminder that you don't have the luxury of time here.
Okay. So it's an instantaneous.
It's an instantaneous, it's chaos, but these kinds of systems that actually movements, a collective movement, so I'm dissipating the energy because it's kinetic energy now. I mean, before it was just stupid heat, okay? Now it's getting more and more, and so over time it'll slow down, but it gets bigger and bigger and stronger. So again, there isn't a simple time scale, a single time scale. It's like at the smallest, it's the fastest, and as it goes, it gets bigger, and it has a appropriate time frame. So I don't know. That's the way I think of it. Okay.
Okay.
So there are a lot of things you don't know. You look at Lai's plot. We don't know what caused what.
Okay.
Okay. In a deterministic world, you would want it. You would want to know it happened because of a stupid baggage handler or whatever, and I can explain it. Okay. This you don't have it. I don't have the sequence. I just know it was nasty, or it happens often. But I also know that those small early events, they get rid of an awful lot of energy. They don't necessarily have to grow big, and I should be very happy that there are those processes. But what I don't know is how much extra energy is. I don't have a good measure of that energy. How metastable is the darn thing? But you know very well that if I look at the traces of how quickly the big storms go, they're getting faster and faster because they're more metastable. Okay, so if you think that long ago you had the luxury of time to calculate where it's going, you don't have that luxury anymore. You probably don't know where it's going to go, and you're better off using an AI approach that looks, okay, this is what the parameters. This is all the parameters I know. This is where it went, and when it hit there, I know the parameters of the infrastructure, and maybe I can calculate the damage. That's kind of what I'm saying.
Thank you so much. But I was also intrigued by one of the slides because you mentioned about this. It gets so organized. One of the typhoons there, very well organized, gathering all the energy and becomes so organized, and yet the entropy is maximum. So it's
Yeah.
very intriguing, that
Yeah,
idea.
that's why I put the chart up, because it's a reminder. What's built into that sandpile model is that it's instantaneous. The whole system is at a tipping point. It's metastable as hell, okay? And you're looking at a competition of different perturbations, and that's what you're seeing. There is no simple differential equation that you can track, okay? You can see these structures and you think, wow, it looks like there's some intelligence going on, but actually that's just some artifact of what's going on, as seen from the satellite. But we have to know that this is really fast. Okay, so that's why I put in there. I always wanted to do this experiment where we look at the storms as they grow, and we measure the fractal dimension. Okay, that's why I put the fractal dimension. Okay, so that may be a measure how quickly the dimension change, may be a measure of the metastability. And yet, it'd be nice if I had some students, we could do it. We could do that now. You have all the data, okay? Because if you try to calculate it using ensemble, you may not get it. But you may be able to see that dynamic and may correlate that to the ultimate damage.
Any more questions? Doc Liz.
Thank you, Dr. Thank you, Dr. Greg Tangonan. I'm so interested in your presentation. In my research, I used electricity consumption to estimate economic impacts of disasters. So, if we look at the patterns, we can see the drop in electricity consumption during disasters, and we can see that, for example, in Typhoon Haiyan, the energy consumption hasn't returned to the normal value, and then another disaster occurred, and then another disaster, and another disaster. So. I see the value of this presentation and research, and I want to clarify about one of the slides, because where you showed the graph on frequency and disruption or intensity, frequency and intensity, and then you showed the VOW and the Baguio. And the slope, is it the slope or alpha? Right. The alpha changed. Yeah. What caused the change in the alpha? Is it the complexity or the structure of the infrastructure?
Yes. If you change if you have a really tightly packed kind of system where all the different pieces talk to one another, so you build that interdependence inside the pile. Then, in fact, it's a very nice, sturdy kind of pile. If you just kind of drop it at random, you have holes in the system, okay? And sometimes that kind of disorder can be very fragile, in the sense that there's nobody sticking to these guys, and so one jerk, one slide of the table, and everything goes. Okay, so it's like the structural coherence and the interdependence locks these guys together, and so it builds a resilience against small things. But if you shake the darn table, like you shake a mountain, or you have a landslide in the Baguio picture, then it's really quite unstable, and so it's a very precarious situation. And as we said, when the exponent gets kind of flat, then what looks like improbable is actually inevitable. So we can look at different kind of situations, and using that critical exponent analysis. We haven't done it, but I'm just saying that that's probably a nice way of thinking about it.
Yes, thank you so much.
Dr. Julie.
Thank you so much for that very insightful talk. I actually learned a lot, and it piqued my interest as well. So just to also follow through from what Liz asked, how about the redundancies in the system? How does that affect the criticality of the infrastructure?
So I think Lai also did an analysis. If you remember the airports, the hub and spoke, there are some airlines that now have decided that the hub and spoke is a little bit too dangerous and a little bit too tricky. So they are having links that are independent of the hub and spoke to build in redundancy, or you might just say plan B, okay? And so that is part of this anticipatory action, okay? And so especially companies or insurance companies, they will suggest to people, I will not give you a policy unless you figure out a plan B, unless you put in redundancy. And that's what anticipatory action is like. Or you do something different, like you start harvesting water because I'm tired of paying the damage for flooding. Okay, I'm out. It's not economic for me to write policies in your area. I will give policies if you make certain changes. And that's what they mean by parametric insurance. Okay, and we can apply it to our farmers, and we're trying to do it. People are trying to do that. But you need a loss model. You need a damage model. And this helps insurance companies a lot in writing the new kinds of policies for parametric insurance. Okay? Realize we're here in Manila Observatory, and what were they doing? They were, in the Galleon days, they're trying to figure out whether or not people are going to lose money on because of the weather. Okay? So in a sense, we're coming back to where we once were about risk. And so, who better than us to figure this out? We got a long heritage.
I think that's all the questions we have for Dr. Greg. So thanks to everyone who joined in and asked interesting questions. To formally express our gratitude to our speaker, may we now invite Father Jet Villarin and Dr. Nino Uy to present the certificate and token of appreciation to Dr. Greg Tangonan. So let me read the content of this certificate of appreciation. So this certificate of appreciation is presented to Dr. Gregory L. Tangonan for his insightful and invaluable contribution as resource speaker at the Manila Observatory's 160th anniversary lecture series entitled AMBAG, Conversations on Science, Service, and Society, given this 15th day of August 2025 at the Manila Observatory, Ateneo de Manila University Campus, Loyola Heights, Quezon City. Signed by Father Jet Villarin, Executive Director of the Manila Observatory. Again, let's give a round of applause to Dr. Gregory Tangonan. To end today's event, may we call on our Executive Director, Father Jet Villarin, to say a few words.
Thank you, Greg. I've seen some of those slides before, but it's only now that I've seen the slides with the man, and it's much livelier.
Ano bang sasabihin ko? Kain na tayo. May pagkain? May merienda, so please stay. Well, first thing, when I saw that graph, one of your first graphs, nakita nyo yung sakuna o disaster, di ba? Baba. And then recovery. And then plateau. And then disaster ulit. Baba. And then it takes a while again to recover. It's a curve actually. Maybe it's an exponential thing. We don't know. But alam na natin yun, di ba? It happens to us. We get sick. Then for a while, we just wait to recover, and then we're back again. But what struck me here was that if it cascades, pag nagpatong-patong, diba, yung problema, nagkasakit yung anak ko, baba. And then, pa-recover pa lang ako, biglang binaha o nasira, nasunog. Pababa ng pababa. And what happens is what? Baon sa utang. Can you ever recover? And that's the question, di ba? The irreversibility we told, because sometimes we just hope reversible yan. Pwedeng, masuntok ka, bigyan mo lang ng panahon, you will heal. Pero may mga bagay na hindi. You lose it. Forever, it's gone. It's like sleep, sabi natin, di ba? Kung 5 oras o 2 oras ang tulog mo, you think you can make bawi. Wala na, it's gone. It's lost. So, physicists have a word for it, and the word is? Hysteresis. Entropy. Entropy. Diba? Fancy word to, I guess, describe the irreversibility of, I guess, the world, nature. If you want to reverse things, you need to put in some energy. Diba? But in a closed system, the universe tends toward disorder. And you say, daya, di dapat. Ganyan ang mundo. Can you grow younger? Pwede mo bang i-reverse yung uban ng yung buhok? Hindi na. Diba? Pag pumuti na, pag pumuti na yan, puti na yan. Diba? Entropy. And this is really what we are seeing. We have to, in a sense, fight entropy. And it can be an uphill struggle, right? And that's why what made me ask is all these non-linear things ay dahil sa konektado tayo eh. What struck me was, sabi niya, yung vulnerability, hindi lang yan sa mga weather, pati sa infrastructure. Yung mga airport. Diba? Halimbawa, kasi konektado sila eh. So, pag nasira yung isa, naapektahan yung iba rin. Diba? It's a web. Now, what struck me was because how do you decrease vulnerability? Actually, you decrease vulnerability by connecting. Because that's how do you increase vulnerability? You isolate. And now we're seeing our connections are also the reason for our vulnerabilities. Diba? So hindi ganun pala kasimple na akala natin, i-isolate lang natin yung problema. Hindi ganun kasimple. And I thought also that this does not just obtain in physical systems, in social systems, corruption. Actually, gusto kong i-plot, Toby, hindi waste management. Corruption versus flooding. Exactly. Diba? And what makes the system corrupt is, hindi lang naman ako eh. Marami ang gumagawa. Diba? Maliit lang yung kinukuha ko. Diba?
Facebook Live.
Ay, Facebook ba tayo? Pwede bang off na yung social media na yan. So, hindi ba? And therefore, I then ask, can goodness also go viral? Huh? Why not? Is it just evil? Why not grace? Diba? Hope. From a few. Diba? Just from a few efforts that are connected. Magsugod ta sa Manila Observatory. Ana, okay, sige. Anyway, so just these are the ripples that from the talk, and I hope that Greg, kasi I guess knows this institution. When he said that exhibit area was the classroom, that was also our classroom under Father Hayden. And I remember Father Hayden used to teach us in that room, and I used to fall asleep because he was such a boring teacher. but Harvard, that's okay. I love Father Hayden. But this place, in a way, has history. So many minds have passed through this place. And I'm just happy to be part, or at one point of the journey of these institutions, we were part of that journey. And I think we will continue. We will continue what others have begun. Hopefully, it will go viral. The goodness, the grace. Thank you. Thank you.
Thank you, Father Jet, for closing the session with such meaningful words to ponder on. So let's use our connections, guys, to spread goodness. So thank you to our speaker and to everyone who joined us today, both on-site and live stream. So for those here today, please help yourselves with some refreshments before checking out our exhibit. Once again, this is Yen, your host this afternoon. We hope today's lecture gave you something meaningful to take away, and we look forward to seeing you again in our upcoming AMBAG sessions and other future events. To stay updated, be sure to like and follow Manila Observatory on Facebook and Instagram for all the latest news and announcements. Thank you so much, and have a wonderful weekend.